it. So, but I won't be starting for another half an hour.
So how will I will be able to log into this, or what was the deal? Should I just keep it on and go later? What's going to do?
Yeah, I don't know.
You want to just let me know? Because I'm not going to look at it for right now. I have some other things I'm working on.
Yeah, well, I'll be starting in half an hour.
You just send me a blurb then? Will you send, okay, I'll write it. I'll write a note to myself. You're starting in half an hour. Okay. So I'll just keep this on then so that I don't have to wind into it again because I had trouble getting on.
Yeah, yeah. Hello.
Hello? Oh, sorry.
How's it going? Thanks for coming down. Yeah. I've got a little professor row if you want to get that VIP.
I'm going to sit at the back.
All right,
Like
all right.
Church.
Yeah. Andreas, you can maybe work out. How do you think I record this thing?
Oh, that I've never done.
It's obviously meant to be like screen share, showcase.
These are all plugins.
Camera.
I like that you're having mimosas.
Yeah. All right. I don't think I'm going to be able to record this, but I can actually do that separately if I want to.
Can I record it on my end?
You might do it automatically.
So speaking of somebody sitting.
I've got you muted. Dad?
Did you mute me?
Yeah. What do you want?
I was just going to tell you a bit of joke because he said it was like being in church. I know it's a Southern joke now. It's quite funny. Fundamentalist guy sitting in church, and the guy goes to visit another church, and they're passing around snakes because one of the things they wanted to do in fundamentalist church is like that if you were really a believer, the snake wouldn't bite you. Okay? So the guy's sitting there as the guest minister, and he says, do you have a back door? And the guy says, no. He says, where do you want it?
Oh, okay. Yeah, I had to run away. What was the link? Was there a link that you got sent to share this?
It sounds like it's automatically recorded and available later. You just go to YouTube video manager editor.
Okay, cool.
Just have it there. So I understand.
Okay, I'll mute myself. Ian.
No, I'm just going to mute you. But what was the link that you got sent, Dad? Can you forward me the email that you got?
I didn't get an email. I just got a note on my computer saying Google Hangout. Okay. I don't see any email. Oh, you got Mom on there too, huh?
Okay.
Ian?
Yeah. Well, I'm trying. Well, I don't know if she's coming, but I'm trying to. Okay, here we are. Wait, why is it?
Oh, you got Mom on there too, huh?
Well, I'm trying to.
Okay. Ian?
Yes. Yeah. Well, I'm trying. Well, I don't know if she's coming, but I'm trying to. My thesis defense thing is just showing my dad.
Oh, you got Mom on there too, huh? She'll really follow this one.
No. Yes. Yeah. Well, I'm trying. Well, how much is it coming? I was getting confused. Do any of you have? Do you have a untitled charger? Oh, I made a little rope here for professors. You're more than welcome to sit there, but if you want to go to the bank. But pick those balls.
Okay, Ian. Ian?
Now I'm. Yeah.
Good luck, man. Kill it. Thanks a lot. Maybe review that. Might remove the professor thing from there. No, don't worry.
Observational studies. That sounds very observable.
Yes.
I still want to be able to. Right, sure. Oh,
Not some of the best Diet Coke money to buy. No. So I came in yesterday. None of the stuff was working. Only that day I had to do some fines.
Oh man!
And they were like,
Oh, the workout.
The worst part was they knew they were.
Okay.
You're gonna lie.
Oh, okay. She gets on. I want to say hi to her. So I saw that.
Yeah, I haven't seen others. I haven't gone.
Okay. So I saw in your announcement it was 9:45, but I think you said earlier.
Yeah, that's what you said.
It is 10.
It is okay. I felt that one is going to the wider people. I
Oh,
put 9:45 so that
yeah.
so that when it comes to 10, they're not running. So yeah, I called it. Okay.
Excited? Have it
I'm
done?
more nervous than what I thought I would be.
Really?
No, this is like effectively. This is the start of my career. Looks like July. Yeah, if I don't really know. But that's definitely the goal. And I feel so. The thing that really was going from all these ideas in my head, which I felt like I understood. Then when you got away from it, then you realize, wait, it's not as clear. So my best at the moment is still, it's definitely still that. It's at the stage where I feel I'm pretty happy with the order. And I can go over. I say, oh, it's really different. And then I do all of that.
Yeah, yeah. But
I can't understand.
no,
I don't.
So the idea is for summer quarter.
Yeah, I actually
Oh, okay.
but I may use paper thing.
See ya.
No, it's exciting. It's exciting. I hope you guys I'm sure you guys will drill down. I kind of went. It's a really tough one.
Call it that. So you just got back from Thailand? Yeah. Very nice. Oh, that's where you are. No, but everyone else is back down. And that's what they so and families they save up for money for visiting Thailand. And that's where they go. That's where they go for have one sister in she suffers through yeah, things are I'm surprised though. The wage allocated to driverless cars is just bigger than
What's that ahead of you?
Yeah. Well, it is quiet.
The one with the
Already? So, yeah. How are you doing? Good morning.
I know. I'm just saying. I'll see the real.
Are you going to Osband?
Yeah, I think that's something.
Right.
How many people are? I don't think I'm the chair.
Do we have a chair? Oh no, because I think I remember there only being four. So there's John, right?
Yeah,
But is there anyone else? You're the
The
chair.
chair? Okay.
Wait, don't you need four people plus a chair?
Yeah, so we have five. Ramesh.
Oh, Ramesh. Okay, yeah. Should we call your mom?
I don't know if she's on it. I think she might be on it on the YouTube.
Okay.
I'm not gonna let them distract me.
Okay.
I'll call them after. Yeah.
How's the movie going? Are you moved over?
I moved over. Okay. It's been stressful.
Have you started?
Yeah.
Okay.
Yeah. So it's been stressful, but it's been really good. Like, managed to get a paper done for ICML, which is basically what I'm going to present the end part of this stuff. But it was really difficult to do remotely. Actually, a lot of some of the experiments I did here.
Remotely from.
Yeah, they were remotely from the United. And so some of the experiments were like super easy to run because I like analyze stuff like running 5 different seeds. Yeah, like, no problem.
You have pretty good infrastructure for that.
Yeah, I like willing to. If you're willing to have a job like that might get shut off and then restart, there's basically unlimited amount of cores. Yeah. Wow. So I don't know if they, but like if you want to do like 10,000 cores,
Yeah.
for half an hour each of them, and you don't mind if it gets preempted once or twice, then you do it. Right.
You can almost fight excavation.
Exactly. Almost. Yeah. They don't bother about it like this. And all these other people are like, oh, it just worked. You kind of crazy something. Yeah. They need to pick, what's the right kind of parameter, cross section.
Well, that's just another.
Exactly.
You don't use anything like spearmint?
Experiment the Amazon question.
I don't know who developed it. It's basically a Gaussian process.
Oh, right. I know what it is. Some of the guys peddle that stuff, but I think that I don't use it. Something simple that works better than book searches is to do on each axis. If you random, if you uniform it, then you end up in it sometimes is better instead of like doing evenly spaced group to take a uniform, a random uniform on that thing, because the way I have it is then you're more likely to get if it's regular, maybe but usually a lot of these parameters are not meaningful, and if you do it uniform, then you don't see like every single cross, but you're sometimes getting more data.
Yeah.
Single. What should I email them?
Totally.
Yeah.
Yeah. It's always so stressful on students when
Organizing and stuff.
when the panel is not here. We had one, it was last week, one of the meeting members was like 10 minutes late. The student was just sweating. So hard to schedule these things.
Yeah.
It's actually pretty good right now in this quarter, but like spring quarter, end of spring quarter,
Everyone's trying.
everyone. Yeah.
Alpha Girl Masters.
Yeah, it's next week.
March.
Korea.
Must be a
It's
lot of
really
buzz.
exciting, yeah. Especially over there, like when people do it at the time.
Yeah. Are you listening to that?
I'm not allowed to talk about it.
Yeah.
Yeah.
You want to play side? I think I'll try to.
All right, guys, thanks a lot for coming. I'm just waiting on 2 of the committee members, so can't get started without them. Thank you all for being so kind.
Yeah. Well, I actually had a student who was kind of not really well. That was just I go with the
Nope. Let's see.
Be careful about how. So they didn't mention that that's the only projects that work. So I thought just what if we like this guy?
Hey, everybody. How's it going? Good morning.
Nice seeing you.
Sure.
See you. So it's time. Let's get started. Ian's going to defend today. It's a pleasure to introduce him, although many of you already know him. One thing about Ian is, one unique thing about Ian is, just to offer some background, I have some experience in finance and some experience in machine learning. And I get approached all the time by students who work in machine learning and want to learn about and work on problems in finance. Ian was the first student to approach me who had a bunch of experience in finance and knew a lot about finance and wanted to get out of finance and wanted to learn about machine learning. So I'm glad that I could provide the bridge both ways. But he's also an incredibly efficient guy. It's been a lot of fun working with him, and I've actually learned a lot from him in this process as well. You know, he was an athlete before he came to Stanford, but even while at Stanford, he was captain, I think, of the GSD rugby team, and would fly around the country playing games all the time. So we have to schedule our work around that. You know, in addition, it's amazing he's only been here for 3.5 years, but he's accomplished so much already. At some point, you know, he was frustrated with the limited computational resources that Stanford has to offer. He'd be flying back and forth to work with his company, Google DeepMind, if he could use tens of thousands of processors at a time. So it's been really fun, and we all look forward to your defense.
Thanks a lot, guys. Thanks for coming. Part of my thesis, deep exploration via randomized value functions. Before I get started, just going to go with a quick few thank yous. Big thank you, obviously, to mom, dad, family back home, all of that stuff getting me started. And a big thank you to Ben, of course, my advisor, helped me get out, switch over from finance to machine learning. I think a lot of the things in this thesis are things which Ben maybe offhand said to me years ago in some of our first meetings, and I didn't really understand. And only 3 years later, after a lot of work, that I sort of got to that level of understanding and able to present these ideas, which he couldn't have. Separately, he's also just an awesome guy to work with. I was worried he was going to tell a very embarrassing story about how he had to bail me out in Bangkok after I got conned into buying a bunch of extremely overpriced sapphires and had to negotiate with the Triad gang to get thousands of dollars back. He didn't bring that up, but it did happen. So yeah, me putting out for a tearful Ben, I lost all my money. That's okay, I'll sort it out. So that happened. Big thank you to Ed. That's why I got him an extra Diet Coke here. They're only the best. Big thank you to everyone at Stanford, MS&E. I think that it's reflected in my thesis committee here. I've got people from MS&E, EE, computer science, statistics, and aero-astro. I don't know anywhere else where you can come in as this PhD student who used to work in the bank. You're like, hey, I want to learn about this machine learning stuff, and all of a sudden you're able to go and do all these crazy things in between all these great synergies. So that's awesome. Thanks to all my friends who kept my social life going. Stanford rugby team wearing their shirt back there. That's great. So yeah, thanks a lot. And hopefully you now see a little bit of what I've been doing, which maybe not what you've seen before. So before we get started, we're going to start with a motivating example. How can we use data science to save lives? And by this I mean, How can we want to make personalized medicine decisions, we want to optimize patient health, well, how can we do this? There are three big concerns. One is we want to learn from the data that we do have. Second, we want to choose how to experiment, how to try out to get new data that we need. When we get a new drug, how do we try it out on new people? And third is we want to plan for health over an entire lifetime. If we take a patient in and we amputate their leg, we might solve one problem, but we've created another problem which they have to live with for the rest of their life. How can you optimize for the long run when your decisions have long-term consequences? More generally, this isn't about health, this PT is very general, but have you ever been asked to make a decision when you're uncertain about what the rules are and your decisions have long-term consequences? If you do, then it sounds like you need reinforcement. So what is reinforcement learning? Well, a lot of people have heard of supervised learning. That's when you've got data and labels, try to learn from that. Unsupervised learning, you've got data, but you've got no labels. How can we make sense of it? And then, statistics does go from machine learning, as most people do. But all of these together are just learning from data sets. That's taking data and trying to make sense of it. But that's not everything in the whole world. In particular, sometimes we have partial feedback. We take decisions and we only learn about the decisions that we take. When you add this in, you get what's called multi-argument. And sometimes decisions we make have long-term consequences. When you add that in as well, you get reinforcement learning. So reinforcement learning is when you have all of these things together. It's a framework for learning to act, learning to take actions in the real world. Three key components. Generalization. How can we learn to do things that we haven't seen exactly before? Exploration. How can we direct our experiments on learning new things? The third is long-term value. How can we plan for the long term? If you want to make good decisions from data, you first need good data. So everyone's talking about big data, learning from data, but we're in systems where the decisions we make affect the data and affect the underlying system. If you're in that situation, you need reinforcement. Reinforcement learning is artificial intelligence. So I'm going to be talking about an agent. This could be a lot of things. This could be a doctor, this could be a robot, this could be a search engine in an environment. That's where they interact. Every time step they see an observation, they learn about the world, they take an action, and they're not just taking this action for no reason. They want to make that money, they want that reward. And our reinforcement learning agents want to get good rewards even when they don't really understand the underlying system. So what do we want from our learning agents? Well, we want that high reward. The problem is you can't really guarantee high reward. You might just be in a difficult situation. You might have a patient with a type of cancer, you'd love to save them. The reward isn't necessarily money, right? But it's just impossible to save them. But you might be able to guarantee low regret. So what is regret? It's kind of the same thing as what a person says is regret. How much better could I have done if I'd have known what the optimal decision is? That's what regret is. Find a bit more. Two main concerns are statistical efficiency. Can we do well in terms of the amount of data we require? And computational efficiency. Can we do well in terms of the amount of computation which our algorithms require? And this PhD is trying to get an approach for efficient reinforcement learning that is both statistically efficient and computationally efficient. So when interest in Markov decision process, it's a simple model for the environment. The agent is going to interact repeatedly with a finite horizon of Markov decision process. It's got S, states, that says what sort of ways can the world be arranged. A, the actions the agent can take. R, the rewards. If I'm in a state and I take an action, what reward does it give me? And P is the transition matrix. How does the world evolve according to the states of that? H is the horizon of the problem, which we're going to assume is fine for all of this things. I can talk about differences finite intent at the end. The important thing is that we don't know the dynamics, but the agent can learn to interact with people. It can learn about it. Our goal is to get good performance fast. One of the key trade-offs is called exploration versus exploitation. At any time step, the agent has a trade-off between trying to make a decision that it doesn't understand very well, but it might learn something. If it learns something, it in the future that might lead it to better performance. But it could try to exploit its existing knowledge, which means, given what it already knows, trying to take these things from weak backwards. So doing this in an efficient way is really the key to statistically efficient reinforcement. So before I get on to that, I'm just going to talk about some really basic things. So it's what we call the greedy approach. I missed the currency. And greedy is pure exploitation with no exploration. And actually, this is the most common thing that is involved. You estimate the underlying system, you follow the policy which is optimal for that estimate of the underlying system. The problem is you may never learn the optimal solution. Imagine if we had 2 drugs to treat a certain type of cancer. We could try the first one out, and the person died. We say, oh, that drug works. We try the second one, the person lives. A different person lives. We say, oh, that drug works. Then from then on, we always try the second drug. That's the greedy solution. Well, you'll never learn about the first drug that you might have just been unlucky with that one person. So the greedy approach is extremely statistically inefficient because we could get an infinite amount of data that we might not learn. So the most common approach to get rid of this is what we call dithering. Dithering for exploitation. And dithering, as it implies, is sort of being a bit indecisive. Sometimes you're normally greedy, but sometimes you take random actions to explore or try to get in here. Common form of this is called epsilon, which is when you're greedy, but with probability epsilon, you choose an action. This will learn the optimal policy because you try everything infinitely often, eventually. The problem is that dithering generally takes exponential amounts of data because it's not directed at things which are potentially important. Just try things at random, and eventually find things at random, like a group of monkeys type Shakespeare, but you wouldn't want to wait around for it to happen. So what's the problem with dithering for exploration? Dithering for exploration is based on this idea that we either know something or we don't know something. When we don't know something, we'll just try out random things and eventually do it. You don't need this machine learning expert to tell you that there's actually a whole other class of things. No. There are things we know we don't know. And if you do that, you're kind of viewed on the whole learning opportunities. You have known knowns, known unknowns, and unknown unknowns. And it's really the unknown unknowns that are the problem. They take a really long time. If you know you don't know something, you can say, hey, I need to find out about that. Do an experiment, learn about it quickly. And so this is what this thesis is about, how we do that practically. So with that, I'm going to introduce the big buzzword of this, deep exploration. What does it mean? I'm going to introduce it in terms of an example. Imagine that our world is this 6-state MVP. Sorry, some of these lines aren't showing up. But basically, the world exists over 3 time steps. You start in state 0. And at every time step, you can either go left or right. If you make it all the way to the left end, you get a small reward. That's what red means, the reward. You don't know. You know everything else about the entire world, except for the reward that you get if you made it to the right-hand side. If you made it to the right-hand side, you might get some information. In particular, this information is about rewards. It's what reward you get if you go there. So a standard supervised learning approach, I'm going to look at the planning and look at entries. So imagine we're at time step 0, we're looking ahead 1 step ahead, 2 steps ahead, 3 steps ahead. We're looking at where we can go. A supervised learning approach knows if it was in state -2, that it should choose the action left, because that would have the highest reward. Yes, it's missing because of the projector. So there should be light gray lines all the way underneath there and all the way to that action. So you can't tell, but for any other state, all of the actions look the same. That's why they're still one. You get no reward. If I'm in state 0 and I go left, well, I can't get any reward. If I'm in state right, I can't get any information. There's nothing useful to do. A multi-arm bandit algorithm improves upon this, because a multi-arm bandit algorithm knows about partial feedback. So it knows if it was in state 2, you take the action, go right, and it would get some information. That's why this is called state 0 and start right. But it doesn't know anything in this state, because going right or left in itself doesn't like that. A reinforcement learning algorithm with iterate can plan for future rewards. So it knows from state 0 that it can get a reward in the future by going left. But it's not immediate that it can do that like that. But it doesn't have any idea about what information you need. So it does iterate. Reinforcement learning with shallow exploration, that's bounded exploration, knows when it's in state 2, it can take an action which is informative. But it has no idea that it could get an informative path of action starting from state 0. To do that, you need reinforcement learning with deep exploration. So that's when you can look ahead multiple time steps and say, oh, there's something I could learn in the future multiple time steps away. Let me go and make a concerted effort to go and learn about that thing. That's what deep exploration is. It's an algorithm that can plan to learn. Okay? And the distinction is exactly the same as planning for rewards in reinforcement learning. Everyone knows you need to do that. But you also might need to plan for exploration if you want to learn. So this is really the key insight of this thesis. It's not new. People have known, they don't call it deep exploration, but this idea that temporally extended exploration is crucial has been known for a long time. But people don't do it because it's usually complicated and intractable. I think it's worth thinking everyone's on board. This is really the key insight of things to keep in mind. So we need to be able to plan for rewards, but we might also need to be able to plan for future exploration. So the weird thing about deep exploration is that we kind of already know the optimal way to do it. Come to this guy on space. You specify your beliefs as a distribution. And you solve for the expected value of exploration and exploitation given this distribution, looking at all future possible trajectories, looking at all future possible concepts and outcomes, wondering what you might know. The problem is that this is fundamentally intractable because the amount of computation you need to know might grow exponentially in the horizon, the number of states, and your beliefs. If you try to approximate this directly, you can fail spectacularly badly, because even if you have just a little bit too little computation, the whole thing won't work. So the whole of this thesis can be viewed as computation tractable approaches to deep exploration. So we want statistically and computationally efficient reinforcement learning. We're going to do this by randomized value functions. The idea is that you treat the future value of your decisions not as a point estimate, but as a distribution. You then sample from this distribution and follow the policy which is optimal for that sample. In part 1, we're going to talk about tabular rasa learning. Now this is learning from blank slate and learning without generalization. I said generalization is important, but it's going to be easier to study without this. We're going to look at optimism based on certainty. That's the principle that's driven most of the analytical progress in this area. We're going to show how you can actually do better than this, better than these traditionally optimistic methods by sampling. The second part, we're going to talk about model-based generalization. That's when the underlying environment has some generalization exploited. We're going to show that you can learn faster in this system. And in particular, it depends on the dimensionality, not the cardinality of the underlying system. Part 3, model-free generalization, where we want to combine the learning and the planning steps in one algorithm. And we show that you can get state-of-the-art regret bounds, even with approximate stereo inputs, but also scale, really large-scale problems, complex generalization, and state-of-the-art results. So let's get started with tabular rasa. Almost all algorithms that are provably efficient exist only in tabular rasa. That's without any generalization of states and actions. All of these algorithms are driven by a principle called the optimism in the face of uncertainty. What this basically says is at the start of each episode, build up a set of possible environments that could be possible given the data you have, and then optimize optimistically over this factor of n keys. You imagine what's the best case environment I'm in, and look for the policy which is best in that best case. And follow that policy. So you can get good statistical regret bounds in this setting, but it relies on efficient analysis and it can be complicated. Another approach, which is actually linked, is through randomized value functions and stereo sampling. The idea is that it's based on constant sampling, which is one of the oldest heuristics for multi-line bandmaps. At the start of each episode, you quantify your beliefs over the environment by distribution. You sample an MVP from this distribution. You solve for the policy which is optimal for that sample. You follow that policy. Actually, we're going to show that this satisfies the same kind of regret bands, but it can be better because statistically it doesn't rely on deep analysis. And computationally, it doesn't involve intractable time step. It just involves solving a single node MVP. So that was a bit heavy on math. I'm just going to go into a little video. It's the first video I've got on the heuristic side. So we've got an example environment here with 6 states. You can't see the middle ones. You can either move left or right. You start on the left-hand side for a small board. Make it to the right for everything in the middle is 0. This needs deep exploration because you need to plan multiple times a day to find the princess. We're going to compare epsilon Greek, that's Donkey Kong, not very smart. So that is. Optimism, this is UCRO2, pick the best possible policy for the best possible environment. And Mario, a hero, is doing sampling, stereo sampling for reinforcement. We're going to watch it. So this is the very first time they go. So they're not really doing anything useful. The world resets every 6 time steps. That's what the blue is. You can see that they're not. But after 100 episodes of playing the game, the posterior sampling approach is basically learning how to make it all go again. So has the optimistic algorithm. It's made it there once. But Donkey Kong hasn't done anything useful. After 1,000 episodes, Mario is making it every single time. Luigi's like he's trying to explore, but he's not doing it in a very efficient way. And it takes like 100,000 episodes for him to make it all the way consistent. Donkey Kong, meanwhile, because all he does is epsilon Greek dithering. Sometimes he makes it there, sometimes there, but he's never even seen the princess. So now we're going to look at the regret of these algorithms. Oh, I can't see that at all. All right, well, it's the regret from learning. Lower is better. We've got 3 algorithms. This is epsilon Greek, that's straight line. Just linear regret, it's not learning anything. UCR2, the optimistic one, it's learning, it's hitting these bounds. But posterior sampling shows up as a flat line, as if it was 0. It's learning a lot faster. Sorry about that. It actually looks like it learns immediately. It doesn't. When you look into just the first 1,000 episodes, you can see it actually takes about 100 times playing the game, and after that, it's learning all optimal policies. So deep exploration is important. You get better by something. So that's kind of jumping to the results, and now I'm going to talk about why this is. Okay, we're learning to optimize this MVP, states, action, rewards, transitions, horizon, initial state distribution. That's where you start. The rewards, the mean rewards is the distribution. This is the mean. The transition of going P. The history, that's all the data you've seen up to time T. So at any time set T, the agent can use the history up. And it's multiple. That this can be over multiple episodes, yeah. So for our episodes of length H, you have to divide this by H. You know which episode. The policy is how you choose your action. So you, given a state and a time frame, you pick an action. And an algorithm, a learning algorithm, maps history of policies. Given the data you see, what's going to be the policy. And it can be a random.
Wait, sorry, what's the role of an episode? The algorithm is supposed to optimize on that horizon?
Yes. Yeah. It's the limit that the value of a policy is the expected sum of rewards over on an NDP on a policy starting from time stage is the expected sum of rewards under that NDP using that policy. So that's an important thing. The policy is optimal if it's the best possible policy. You have the highest value. The regret of an algorithm with time T is is the sum of these delta k's, where delta k is the regret x of k. And that's, okay, this is important. This is the expected shortfall in value from following the policy UK in the true entropy n star rather than the optimal policy u star. That's what your regret is. So if you have no regret, you're doing as well as you expect. It doesn't mean you're going to do really well, it doesn't mean you're going to cure cancer, but it means you're going to do well as a doctor with perfect information.
Rho S states
Yeah, exactly. It's really not. Rho S, we assume that every H concept you get thrown into a new state. And you have no control over that. So that MVP is the final.
S is a Rho S is over initial state, or
Over initial state. So
but this is still with respect to finding what mu is, right? It's kind of a local function.
no, because our world kind of resets every H concept. Exactly. Exactly. It can be just starting. I'm going to give a little bit of a flavor of how we get it right, how we do things. But this is really quite a high level. I'm going to probably have to repeat this point. So in any episode K, you can look at the regret, which is the value of the optimal policy minus the reward of the policy which you follow. Now this is for optimistic algorithms. And for serious algorithms, we have this imagined NK. And what I'm going to do is I'm going to add and subtract the value of this imagined NK. Okay. So I imagine the world somewhere, and then I imagine it. So if I add and subtract, it's 0. Well, that breaks it, this regret into 2 terms. The first is called the optimal regret function. That is the value of the true optimal policy minus the imagined value of the policy which we actually follow. That's what that is. This term is the concentration. This is the imagined value of the policy we follow minus the actual value of the policy we follow. And with optimistic algorithms, optimize this problem. It finds the policy and which is best, creates the highest value. And if the true NP is designed so that it lies within this family of NPs, then this optimism curve is negative, not positive. Posterior sampling, in the Bayesian way, I write UK for the policy which is optimal for NK. Well then, conditional on any data, here I use K as HK is the data available at XK. Conditional on any data, the sample endpoint is equal in distribution to the true endpoint. This means that the expectation of this optimum is 0, because these are random variables which are identical. So you need to figure it out. You have to have that way, right? This is only assumed that the n star is distributed according to the actually, we're going to talk about some ways in which we can get away from that. But at the moment, that's what we're assuming. So this means that if n star is distributed according to its prime, we can bound the expected regret of the posterior sample by just looking at this concentration regret. The same way as in optimism, we just look at this concentration regret. Why is that useful? This only depends on the policy UK flow rate. It doesn't depend on the optimal policy U star, which we don't know. That's why greedy algorithms might not converge, because they get loads of data about the policy UK, but they don't learn anything about U star. And so to finish this proof, you use the Bellman operator. You say, oh, the value of concept 1 is equal to what I expect to get at this concept plus the value of the next concept. And you can sort of break this down. You can break that down to these terms plus your estimation error in the rewards plus your estimation error in the transitions. Okay. And you know that the estimation error should concentrate because it's of the thing that you actually see. Okay. So I'm going to show that posterior sampling, when you view it in this way, it's really similar to these optimistic algorithms in a lot of ways. you're happy to take things in terms of Bayesian rather than just looking at standard. So the way these, you're just back here. So you've got all these terms. This is the estimation error in the rewards, estimation error in the transitions. The transitions are really the target for in reinforcement. So the key part for your analysis is doing this. And so these optimistic algorithms that typically are, they normally conclude by bounding the error in the transition and an error in the reward, the value set, like a holder dependent. So you take this norm and you say, oh, well, this thing is some concentration of it's like square root of n, the amount of times n is the amount of times it sees this data, and s is the dimension of how you transition. And this, the value of this thing is of order h. And then you get a regret bound that looks like this. I have a theorem from our thesis which says that if you take any optimistic algorithm and you can create this regret bound that holds with high probability for any specific MVP, if you can design that sort of optimistic algorithm, then we can follow these arguments and say that in expectation, posterior sampling will satisfy the second analysis. Modulo effect of truth. And what's the basic idea? You say, well, conditional on any data, the true MVP is distributed report, the sampled MVP, and then you can, any concentration is already given the true MVP, it also applies for the sample. So you can perform sort of analytical juggling. So what's the problem with these optimistic algorithms? Well, there's the first thing. First, our analysis is in terms of P, which is exponential, B, which is exponential, B is the value. But all you really care about is the future value, the transport field, where you're actually going. So you're learning S scalars instead of one scalar. That seems bad. The second thing is we've got loose bounds on each one of these concentrations. We're bounding in terms of L1 norm, but maybe the correct bound should be more like a KL concentration. And I have a little diagram back here, like 3D simplex. These are our L1 bounds, and maybe the KL looks more like an ellipse. The bigger problem than even that is that we're doing a union bound across each state of action independently. These algorithms say, oh, I bound my error in this state in this action. Well, then across the whole thing, they bounded the resulting MVP by the bounds of each state action independently. But that might be far too loose for what you actually get. You get a big hyper-rectangle instead of maybe an ellipse. Because if you were 5% likely to have a certain level of error in one state action, you'd be extremely unlikely to get that level of error in every single state action. The worst part is the computational cost. Even if we could design these confidence sets that were ellipsoidal, both on each state action, both across all the states and actions, the resultant optimization problem would not be tractable. Because you can't do linear, these algorithms don't work because of linear programming over L1 balls. If you have an ellipse, it might not even be trackable. And to give an idea of how big a difference this is, I'm going to plot here the volume of a unit cube and the volume of the sphere inside that cube at given dimension. You can see that even for small dimensions, like 9, it's not very big number of states and actions. The sphere picks up almost no volume inside the cube. You plot this on the logarithmic scale. The sphere is a vanishingly small part of the cube. That means that when you use these union bounds, the confidence sets can be exponentially specified for the true underlying probability distribution. If you use posterior sampling, you always sample from the correct distribution. If you use a union bound, you can be exponentially misspecified. So we're bringing in a new notion to capture this. It seems, how John said, it seems a little bit weird that everything we do here is totally dependent on trials and its exact purpose. We don't have a good way to talk about optimism in terms of distributions rather than points. So we introduced this new notion called stochastic optimism. And it's got a few equivalent things, but one definition is X random variable is stochastically optimistic for Y, if and only if, for all increasing and convex utilities, the expectation of U of X is greater than the expectation of Y. This is kind of a dual notion to second order stochastic problems. It's sort of the other way around. Another way you can write it is that X is optimistic for Y, if and only if you can write it as something positive plus something E0 plus Y. You're allowed to be more optimistic. You're allowed to be more spread out. And you've got a really kind of a weird technical result. That this relates the posteriors of the Dirichlet distribution with an approximating normal. So this, I'm going to have to slip over. The idea is that if the underlying system has a Dirichlet file, and I make correct posterior inferences from it, well, if I instead used an incorrect file, that the system was Gaussian, and I always updated it as if it were Gaussian, then this result says that the Gaussian approximate posterior is always optimistic for the underlying Dirichlet. This could be useful in a lot of things.
So this is saying that you can get this kind of conditional optimism for all kinds of steps.
Yeah, so that's obviously a very, I actually, in the thesis we talk about, I don't think that this is necessary. This is what we've proved, that for this strength linked class of families, you'll always be optimistic, no matter what.
Is there any intuition? I mean, is this like just super specific to normals and Dirichlet?
Yes.
Yes.
Probably much more general than Dirichlet.
Okay, so we think it's much more general. Okay? But what have I actually proved? It's a very specific result. Because
Sure.
proving the more general thing, it really feels like it's true. And I can talk about that.
So somehow the normal is so clear that it's like, because it's conditional distribution in place so nicely, it's always optimistic. Maybe a lot of
Exactly. That's all I can talk about.
So you should always show, we should always show everything how
So I don't think you should. We're actually going to see an algorithm that uses this approximation. What I'm going to show is that using this approximation of the incorrect Gaussian distribution is not as good as using the correct form. But it's better than a union bound with this geometric square. So it's somewhere in between. Not quite. Exactly. Yeah.
It's a way of creating algorithms.
Yeah, exactly. All right, not just use it. But what's the takeaway? The takeaway is that actually a lot of this analysis doesn't really require that we use the exact posterior. It requires that we're sampling for something that is, in a sense, optimistic. We'll get back to this later. And the cool thing is if we use this weird number here, we can actually remove an S dependence in our analysis. Even if we use the same algorithm, we just compare it to its Gaussian. We show the Gaussian concentrates something that doesn't have an S. That's actually what it is. And you can get an efficient algorithm just by using the Gaussian. So now I'm going to go to some experiments. Can't really see this here, but we've got n states in a row. Action left is always successful. It's deterministic goes left. Action right is only successful run max 1 over n. If you get to the right-hand side, you get a normal 1-1 reward. On the left-hand side, you get a normal 0-1 reward. So the optimal policy is to go right, but it's kind of difficult to get there for long chains. And it's hard to learn. This needs deep integration. So this is a length n equals 5. PSRL is sampling according to this theory sampling. Gaussian PSRL is using this Gaussian approximation that I just said. And UCRL is using this compensation. You can see PSRL is the best one in Gaussian PSRL. So this is n equals 5. Maybe not that big of a difference. Keep in mind this gets a regret about 6,000 after a million things. That's on n equals 5. We now make the chain bigger, n equals 10. The difference between their performance is going on a lot bigger as well. Again, PSRL is the best. UCRL is looking really bad. So although this is efficient, this is like the best algorithm that exists. It's better than RMAX, it's better than It's really just terrible. And that's only like 10 chain. This is like 20 chain. UCLL that doesn't even learn how to get million steps. These graphs look a lot better. UCLL is classic. UCLL is so bad that I had to introduce a new version called rescale UCLL. The idea is, okay, we'll use the analysis from UCLL to playbook the algorithm, but I'll make the confidence right because I just know that I did a bad analysis. So this is rescaled by 0.1, 0.01. So the 0.1, okay, that's really better. These ones learn a lot faster, but they don't always learn. Not every seed. Because I've rescaled them so thin, they're not always optimized. This is a length of 20 chain. Length 30 chain, then I have Gaussian PSRL has this nice UCLL. UCLL is not really working, but PSRL is really strong. N equals 50. All these things, they're doing so bad. PSRL, really good. When you look at N equals 50, we're getting about the same performance in learning as UCLL did on length 5 chain. What priority did UCLL use? The Jeffrey's prior for transition communication. Jeffrey normal 0.1 for the words.
So the three things, the model is fixed.
Model is fixed. I'm using it that way.
Is there any efficient logic on that?
More time.
Yeah. It's a good day.
Oh, it's not actually like just take some. So we're actually going to see this here. It's a scaling issue. So now I'm looking at the log of the length of the chain against the log of the time of the average of the lowest one. And these are the different versions of UCLL. This line is a slug 4. This is a S times H. You can see that although I rescale it, I don't really help the scale. They do a bit better, and actually a lot of these C's don't converge. But scaling follows is good. Now, we do the same thing with PSRL, Gaussian PSRL. These slopes are 4, 3, and 2. We've actually proved the bound that these two satisfy 3. We have a hypothesis that this one should satisfy 2, kind of a hint of proof why it should be. But this is born in code. And run over 5 C's, take the maps. Pretty convincing. These are not regression, but I pick these levels to make you think that what I'm saying is right. It's fine. Okay, cool. So, success. We've got a new analysis, show PSRL is efficient. We've got better bounds. We hit this square root SAT regret bound. It's better than anything else that's called. It's you can't do an algorithm better than the square root SAT regret bound. It's optimal statistically. We only need to solve a single MVP. If you had an optimistic algorithm that did this, it wouldn't even be tractable. It wouldn't be confidently tractable. But if you design one, well, your proof now works for the PSRL. Congratulations. So this is amazing, right? There's great success. And it's robust to any approximate bound. Because if we don't solve the MVP exactly, these bounds just shift by the amount of approximate bound. It's great. But it's still not really useful for anything. Why not? It's because it's tabularized. We don't have generalization. You need to learn an amount of time that grows with the number of states, number of actions, number of time steps. Because you learn them all at the end. Practical problems have a lot of states. They have a lot of actions. My position as flying a plane, symptoms, that's why I do all these things. I realize I'm running about this. So our only hope is that we can learn to generalize from our experience. I said this was one of the important things of learning, and I just totally ignored it. Well, now we're going to get back to it. Optimism in the face of uncertainty, as we've seen before, is almost always intractable with this generalization. But this algorithm perceives this happening, randomized value functions, it scales naturally to generalized problems. So the first thing I'm going to talk about is model-based generalization. That's when the underlying world, I learn about the world, and I can generalize from my experiences. First example of these are the one is on factor. So imagine that the state can be decomposed into n state parts. And over a single time step, each one of the parts of the MVP evolves. But the way in which each piece evolves only depends on a small subset of the other underlying. It's an MVP with conditional independent structure. I'm going to give an example. Imagine you've got a long production line, 100 machines. And each machine can be in 4 different states: working, not working, not working, working. And you have 5 different actions. Power, repair, guide, well, then the resulting state space is 4 to the 100. The number of actions is 5 to the 100. This is huge. More than the number of atoms in the computer. You're never going to be able to learn this through calculator learning. But if you know this factory structure, then you can get regret maps for fields around that take this exponential. But that's the idea. More generally, if you have a system that sort of smoothly parameterizes, and you know that the rewards are in some function function, then you get regret bounds in terms of dimensionality, not cardinality. So the example is if you know these families are priority, you get this kind of dimension. You need a slightly different notion of dimension from standard supervised learning models, but it actually matches up pretty nicely with intuitive notions. So if you have a d-dimensional linear quadratic regulator, that's kind of a canonical example, well then you get d. That's good. Okay. Whereas if I had to discretize everything, in dimensions, it would be exponential. So these were 2 papers, took a lot of math and stuff to really get down to one slide each is all you get. So a great success again. These are about as good as it gets. You get learning with generalization. We're robust to any approximate plan.
Oh, you need one slide.
Oh, for that?
The draft?
Yeah. All you need to be able to do is sample from your beliefs and do approximate planning. If you can't quantify your beliefs, you can't solve your beliefs, even if you knew what they were, then you could have never done the learning problem anyway. You should have given up. So in some ways, this is kind of the best I could ever hope for. But the problem is that maybe planning itself is impractical. Okay? Even if you knew how the world was, you might not be able to solve it. Go is a perfect example. The game of Go is really simple to state. But even though I totally know the rules of Go, you can't play it. It's too complicated. Planning is hard. Okay? So we've reduced learning to planning, like the near optimal way, but that's not really good enough for solving real problems. Depression again. Maybe we can do better. Maybe we can sort of approximate the value of it. All we need to be able to do is sample random value functions which are optimistic. We have a definition of this. It's simply stochastic. And we just need to concentrate with the amount of data. As we learn data, we need to concentrate on the real thing. So that's where we get onto model theory and So to do this, I'm first going to talk about another algorithm called least squares value relation. So when you model the value function as a linear combination, how good the world is a linear combination of numbers. The way it works is you do a linear regression for the value at this time step should equal the value, the reward I get at this time step, plus my expected value at the next time step. Least squares value relation does this linear regression, backs it up. Typically, they explore with epsilon 3 or Boltzmann 3. This takes an exponential value. Our algorithm, randomized least squares value relation, is almost exactly the same. But instead of just doing a standard linear regression, solve the linear regression, but then we perturb it by some Gaussian noise. And this Gaussian noise is what you would get from a Gaussian theory, treating everything as if it was Gaussian. Now this might look familiar to what we did before. It's using this Gaussian approximation. But the difference here is now we have these basis functions, phi, which may generalize across different states. You get exploration by the noise in the sample. And actually, if these basis functions are just the indicator for each state action, then we're basically back to what we had before with the Gaussian CSRO. There's a slight difference because but it doesn't make a big difference. Basically back to the provably efficient. This is provably efficient in some settings, whereas this one is always provably inefficient. So now I've got another one of these examples. No rewards on the left-hand side, one reward on the right-hand side. If you use epsilon 3D, you both can remember. But the agent doesn't observe the state in this one. It's going to interact with the environment with a random basis function, a set of random basis functions. I generate k of them, and they're guaranteed to include the true value function, but each one in itself is not important. They're normalized Gaussian subsets. So when I look at the learning over the episodes, this is the regret epsilon 3 RLSVM. And I extend this out to a million episodes, epsilon 3 still has a length. This is a length 22 with 10 features. So here, I look at, okay, that's very good. How does this scale with the chain length? This is the length of the chain going from 0 to 150 at 0. This is the number of episodes until we get 10 perfect episodes. Here's a lower bound on how long it would take any given strategy. Here's a lower bound on what it would take any collaborative strategy that learn each state and action independently. This only has 10 basis functions. So it learns a lot faster. And it scales like linearly. Now I look at how the same thing scales with the number of features from 0 to 100 on a length 50 chain. Well, it looks like it learns, almost immediately when we've got only one basis function. That's obvious. But as we get more and more basis functions, it seems to kind of go linearly and then level out around 50. But 50 is like the underlying complexity. I don't know for certain, but certainly it's not exploding. Now look at this. This is the log plot. This is the chain length against the number of episodes. This is the 5 features, 10 features, 20 features, 30 features. It scales really nicely. Our hypothesis is that it gives us polynomial with generalization, where the true value function lies within the span of the picture. I haven't proven this yet, but you can see all the seeds here. It fits really nicely. But the real world, the value function, doesn't lie within the span of the basis function. That's just a fact. Okay? This is a worrying thing because we want to be able to do well even when we're using an approximate. Well, the nice thing about this simple example is we know what the value function is, where we play it. And so in this problem here, I run this exact same problem on a length 20 chain, but I perturb the basis functions by random noise, Gaussian noise of standard deviation rho. So that when we have this rho bigger than 0, the true value function does not lie within the span of the basis function. And I look at the number of episodes until 10 rewards. And blue means that it learned before 10,000 episodes. And red means that. And the kind of important thing is there is some region here where it's robust.
So what you might hope to see, and maybe I'm just missing something, is that even irrespective of what basis functions, we sort of are guaranteed eventually to do this well as the best
thing in that class
with those basis functions.
Yeah.
Are we going to see some result with that? Is that possible?
I don't think it's true, but I definitely haven't proven it. It would be really nice if we could.
So we don't know either way.
No. We're now at the stage, by this stage in the thesis, we're beyond any of the stuff I can prove or have proved. This is all just conjecture and empirical results that this can use problems with generalization. Interestingly, I don't know of any other tractable learning algorithms that can even do this empirically. So it's a step above in that situation, but sure, proof is not there. So this is cool, but this is still really a toy example. So we start, from now on, we're back to interesting stuff. So friends of mine who came for a bit of a few videos and see what I did, you can tune back in now because it's about to get more interesting. Learn to play the game of Tetris. Classic video game. We use a set of linear features, the height of the columns in each row, the difference of heights, max height, the number of holes. And we use randomized least squared valuation, and we compare it to least squared valuation with epsilon 3. And, okay, you learn a better policy. But it's better, but it's not like exponentially better. Maybe Tetris doesn't have this sort of structure with deep exploration. It's not even clear that it's important. But even in this situation, it's doing better. We then made a special version of Tetris that only has S and Z pieces, little S pieces, little Z pieces, and it only has 4 rows. So it's really, really difficult to clear that sort of thing. When you do it on this sort of game, you learn a lot faster and you learn it better. This sort of effect is magnified. If you make it wider and shorter, or made a Tetris where only, instead of clearing one line at a time, you clear 3. You didn't get any ore until you lined up 4 lines. Then deep exploration is really good. But to give you an idea, this is after only 100 games of playing. With those features, it really plays really well. And actually, it'll clear 4,500 lines on average. Which is pretty good. It's kind of exciting when you see this real game that you play and it's playing really good. So the next thing, this is actually Zen did all of this. We've got a model for a recommendation system. We've got a library of 10 categories. The agent can recommend 5 items. Users like or don't like what they see. But normally people don't treat recommendation systems as an RL problem. We make it an RL problem because we make the preferences be a function of the user, the items, and what the items that the users have seen before and whether they like it. So to give you an idea, it's like, oh, I'm watching Breaking Bad. Well, whether I like season 2 of Breaking Bad depends a lot on whether I've seen season 1 of Breaking Bad, whether I like it or not. And this model allows for account for that. So if we look here at the per episode regret, 0 is here. And this is least squares valuation, randomized least squares valuation, compared to LSVI with Boltzmann exploration, which a lot of people think is way better than XM3. We see we learn all near optimal policy, and they really get stuff like that. Interestingly, we compare this to the optimal Bernoulli bandit strategy. That gets this with the optimal linear bandit strategy. The optimal myopic strategy, that's the one that doesn't take into account the future rewards. And we can do better than that. So this shows that, hey, reinforcement learning can be useful in a recommendation system. And in that situation, deep exploration is really important. So those are 2 really interesting things. But everything we've done here has been linear features. We assume that we have some features and we know how to work within that. But learning good features is really important. And that's kind of the idea behind deep learning. We're now going to combine deep learning with reinforcement, using neural network to learn the Q values directly from raw pixel inputs. And so this was a DeepMind thing, superhuman performance on Atari games. They got raw pixel input, agent actions, like programming language. Learn through self-play, but it uses epsilon greedy dividend. There's one thing you take away from this, it's like, oh, that's terrible, right? Well, they got it to work, so it's obviously not always that bad. But we hope we can do better. But how are we going to do this in a neural network? Well, we use the bootstrap. The idea of database simulation, approximate your population by a sample distribution. A simple way of doing this is you take your data, you take a random subset of the data with replacement, and you estimate all that data. Does this work for neural networks? Yeah, it works okay. So this isn't showing data, but we generate this sort of noisy data. It's blue. This is a Gaussian process regression showing the mean and the variance and a sample to see a sample. This is using a deep neural network with ReLU hidden units, and you get a kind of qualitatively similar. This is really not showing up. The idea is it's capturing some intuitive notion of uncertainty like that. It's all right. So what's the algorithm? Instead of one Q network, we branch off K heads. So we share the convolutional neural network, which does most of the computation. Then all of these features, we use 2 or 3 layers of neural network. And each one of them learns its own representation on a bootstrap sample. And the algorithm is exactly the same. At the start of each episode, you randomly pick one of these estimates to follow. These approximate our posterior. And then you follow that head, that sample, as if it was really different. You get known unknowns by this bootstrapping process. You get deep exploration by committing from the entire episode. So by the end of this, you've got to be sick of these chain examples, but we got one. We want to see if it can work, right? And we're going to do it from raw pixel stuff. Because now the state, instead of is not passed with a 1 hot, which is 1 0 0 0, or thermometer, which is 1 1 1 0 0 0. state encoding and see if we can learn from the raw pixels. And if you use shallow exploration or iterative, it takes exponential time to learn in this situation. But if you're really doing deep exploration, you hope to do better. And sure enough, we see this. Here's the chain length. Here's the number of episodes. You can get 100 episodes. This is bootstrap DQM, going very nicely. It looks exactly like we saw before. Here's DQM, it's F1 never worked. Here's what they call Thompson DQM, which is when you resample every concept. It doesn't do deep exploration. It's directed, but it's not deep. That doesn't work either. And the lower bounds, so they don't. The first thing, now we're going to get to some authority. We're going to see it on the real thing. We're going to see how bootstrap DQM can drive efficient exploration. So we've got different I'm going to show you things first. So this is actually the agent pipeline from the raw system. We've got blade, explosive, safety. This is the 10 different heads playing. So you can see that although every single head is playing the game, they're not doing exactly the same thing. Each one is playing all right, but they're doing different stuff. And that's how it's able to do this diverse exploration. If each head learns to try different stuff. Pac-Man, this is playing Pac-Man. Yeah, it's pretty cool to look at you see these things. Just a few years ago, this wasn't possible. But now they're all playing Pac-Man. And although they all look like they're going the same place, if you like zoom in on this area there, you can see that they don't eat the exact same pellets. And because of that, they might be able to learn better state representations, better invariant. This one's sequenced to the fish, saving tigers, taken to the continent. And so, bearing in mind, this is all just one single algorithm, no tuning for each individual game. Throw this thing out, and it learns to play just from the pixels and the score. And hopefully it's clear that these are like a wide range of things.
So these things slow.
Oh, they learn faster. Yeah, you put them on the simulator. So actually, you're going to see that here. So they certainly don't learn that. They get millions of frames.
So like if you made a robot body, you do like a robot body.
Yeah, it can be really just.
Once he shipped from the factory, played millions.
Exactly.
Yeah, if you shift it back then the hardest thing would be him.
Yeah. So apart from exploration, this kind of approach might be useful because we have some idea of uncertainty. We can use the different heads of the network to represent uncertainty. So here is it playing the game Breakout, and on the right I've got visualization of voices. And it's using an ensemble policy where each head gets the vocal reaction. Green is the one that's chosen, blue are like close to the chosen. And you can see that actually this captures some sort of reasonable motion. As this ball is moving away, you go on certain. But when pressure is really on and this ball is coming down, they all agree, go left, right? So although this is useful because maybe in a lot of situations you want to know when your algorithm is not certain. Like Presto, it actually gets pretty down to the game. Learns that make this tunnel on the side and just absolutely demolish the high scores. You can see this across a lot of different things. Eating away, this kind of gives you a way to know what it's thinking. It's just brutal. It's just absolutely brutal. This was, so if that gets out, if that robot frame gets out, cool. So I've got more videos that are implement this, but here's just you might wonder, okay, how many of these different heads do you use? Well, this is the learning curve. So you do the boards and breakout. That's the Miller. That's with 2 heads. That's with 5 heads. That's with 20. You seem to get decreasing for these things. And that kind of makes sense because labs. But when we look at the early learning of these things, we can produce a really big speed up. This is the number of training steps. This is 4 steps up by now. Notice that this is measured in millions of frames. So unlike Tetris, where you break 100 units, that seems like kind of reasonable. This is still taking like 10 million frames. So that's maybe 100,000. Not very good. Why is that? That's because we're having to learn. We're not learning from tabula rasa, we're learning via generalization. We have to learn vision. Tetris, we're giving it the basis function. It's kind of an intelligent product. We get faster learning, better performance, more robust, with fewer of these really bad across a lot of things. So this is looking at the early learning of a lot of these things. It's the same algorithm. You can see that the bootstrapping again is really working a lot faster. It's all a single configuration for a model. What's a conclusion? If you want to learn fast, you need deep exploration. If you want statistically efficient reinforcement, you want algorithms to learn, but they'll also learn the full health. You need deep exploration. This theory is sampling for reinforcement learning of this optimal scaling for data and computation, these tabular entities. That's sort of a theory part. We actually show that we can extend this through randomized value functions to domains with generalized. And we get state-of-the-art empirical results and large-scale benchmarks. So we're able to get some of these aspects statistically and computationally. And that's the end of the thesis. Thanks a lot.
I guess we'll take public questions. Yes.
Could you comment further on methods of influence learning for the group goal?
Okay, so deep reinforcement learning often gets used to be deep learning plus reinforcement learning. Maybe they need to have deep exploration before they can really be called deep reinforcement learning. But Go even had that. But deep learning is all about learning your features. A lot of standard machine learning used to take, you had your features you were given, you tried to do the best given the features. With deep learning, it's all about trying to learn these features as well. So why that's really important in Go is because it's this game with these white and black pieces. It's really hard to come up with any reasonable features to describe who's ahead in the game and who's not. And using deep learning in Go was really able to try to learn these features organically through looking at lots and lots of data things. And that was really important because it allowed you to express reasonable value functions, which previously had not been able to do any Yes?
Why is it you seem to be real? Realism is essential.
I don't think I know exactly what is seen under Okay. Yeah. I feel that something like that might not always work well. I think that that's similar to some of these approaches for Bayesian optimization or bandits, where you need to, those things can work well on specific problems, but you can someone's design where it doesn't. But again, I maybe don't. Okay, maybe let me clarify. Okay, so I kept going back to that chain, right? Summing of this flavor. And imagine if there's no reward here, and you don't have to know that you make it all the way to the end to get the reward. So if all you did was this process that someone's jumped around, you have no way to direct your jumping to meaningful spots. Okay. So your space of potential policies which you can follow over any episode is of the order of the number of actions to the power of the number of states. Okay. So that's like 2 to the n is chain, where n is the chain. So if all you did was jump around, you have to jump around in this exponential space. But if you want to be able to learn in time that grows polynomially with n, then you need to really direct your exploration. You need to be able to direct it in this situation to things which are informative over multiple processes. And that's why you need deep exploration, something like annealing, epsilon annealing, even if you choose well, is not important. Any final questions?
Yeah, I was just wondering, it's about something here. Your, so that this example, essentially, there are only two essentially features, essentially, 2 choices after that. Your
Yes, yes. And so there are lots of different ways, and I think that that's really what most reinforcement learning and practical machine learning people have done. They know that deep exploration is important, but you don't have a good way to do it, so you focus on being able to rephrase your problem in a way that deep exploration isn't necessary. And in a lot of situations, that's necessary. So if you looked at this and you said, oh, my only 2 possible choices are go all the way to the left or all the way to the right, then I've only got a very small amount of things to consider.
my question is, when your average, even if you should cover the end states,
Yeah.
your average,
it doesn't work like that, but it's you could make something like that, but what it does figure out is that the optimal set of decisions is to go on. That I don't know if you're learning about that.
yeah, so I mean, you keep this problem for this kind of problem, like you could, the end itself could be a right number, or 2,
I think that's true. I think you could do that, but the point is this problem's not interesting. No one cares about these.
well, but usually if you have a block, and then that could be or something. Only if you then maybe that's a little block.
Yeah. Okay, let's thank you, Anna. Okay.
Well, thanks.
I'm gonna go.
You need to run again. I think you might not sound sensitive to what we said. Probably should cross it.
Yeah, we're gonna do around. I don't know. Someone's. But I have that.
I'll experience it.
No, all I need is inside. Inside. Yeah, I'll send you these myself. I mean, I know. Yeah, no, I haven't. I was really worried that all. So the theory is that they need to, every far apart. I think they're really fun. It's just small differences. It's not like small changes. Almost instruction. Look like that. I think that's now I'm making use like the double. You think so? You think so, right? Yeah. I think.
Yeah, we should probably.
Yeah, because I have them in 11:30.
Problem with me.
Well, I talked to him about his offer, and it was very good. Oh, it was ludicrous. Yeah, it's like, all right.
There's it, shut the door. Started.
First question. What are they offering? What? What are they offering? Yeah, I definitely could have gone that. Well, what did they? What? I mean, is it too late to get it higher? It's too late for now, but maybe by the end of the year. When it comes, because
When you pretend to read.
Exactly, and there's now OpenAI, so we can do this.
Yeah.
So they kind of like, I think they were trying to put a bit of pressure on me to sign because they knew about OpenAI.
OpenAI is good, right?
Yes. And so they knew about it and I didn't.
You're pretty easy going.
Yeah. But
Why? Why didn't you?
because I didn't realize how much you could milk.
No, he did. That meeting. Have you really talked about this?
I didn't know. I didn't realize.
Really?
I also was a bit nervous. I was a bit nervous.
How do you know? How do you know there?
No, I mean,
I think I was a bit nervous because at some point I decided that I don't do it. And I was like,
yeah, let's say that's it.
and then the guy then
Thomas, who's the CEO, is really good at putting sound. And I do think he's really inspiring, but he sort of said, like, oh, I think you're special stuff. Short but special. I know, and then I'm like, okay, well, this is great. I get it. You know, I go now. Also, at the time, I hadn't finished some of that stuff, so I kind of wanted to drive that.
All right, we should probably get started since I'm running.
Is your mom joining us?
No. So,